On page 18 in your notes, this is the example 3 that I would have liked to have gotten to in class, but I didn't want to just rush it or only half do it. So it's talking about the length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, a mean of 266 days, a standard deviation of 16 days. So we're going to find the probability that a single randomly chosen woman, a pregnant woman, has a pregnancy that lasts for more than 270 days. So again, this is something that's not from this unit. I mean, it applies, but we've been doing this before. It's just a normally distributed population, so I'm going to note that the center is 266, distance to the point of inflection is 16, and this is individual measurements. These are the lengths of pregnancies. We're supposed to find the probability that a randomly chosen pregnant woman has a pregnancy that lasts more than 270 days. That's like a fourth of our standard deviation. So that is pretty darn close to, that halfway mark anyway. I don't know why it's doing that. There we go. So I'm just going to try and squeeze in here really little bitty. My cutoff is 270. So that's the area that I'm going to be trying to calculate, the area that is above this. It should not be unusual based off this information. I can already tell. It shouldn't be unusual to find somebody whose pregnancy lasts longer than 270. So to calculate it, finding the probability that a randomly selected individual X is more than 270. So I'm using normal CDF. On the left, I started shading at 270. The right was technically positive infinity, so I'll just throw in 1,000. The mean of this particular distribution was 266, and my standard deviation was 16. So when I put that in my calculator, I get 0.4013. So like I said, very not uncommon. 40% would have these types of pregnancies. That's for an individual. Suddenly, if I change it to a simple random sample of 6 pregnant women, and X bar is the average pregnancy length for that sample, first I just want to know what's the mean of that sampling distribution of sample averages. It's the same thing as the population mean. Still 266 days. So they would be centered at the same, but if I have a sample of 6, your variability should be dramatically cut. But before I find what it actually would be, I need to confirm my 10% condition. And this is not one that is a big assumption. This is a sample of size 6. And that's definitely going to be less than 10% of the population, which is all pregnant women. So because that's true, then I can go ahead and find my standard deviation. So the standard deviation of the sampling distribution of sample means is just the population standard deviation divided by the square root of my sample size. So the population again was 16. My sample size was 6. So I'm going to drop that to a standard deviation of 6.532 days. Now remember, this is describing the typical distance between an average of a sample that is collected from the true population average. It does ask us to interpret this one. I didn't feel like... I did it in the wrong location. I did it down here. Didn't I? What's going on? Oh, that's why, because I put it up here instead. I was trying to be lazy and not write it out, and I wrote it in the wrong place instead. So that's fun. So that's down here, and you can't read half of it, and I'll go and fix A before I actually upload these notes so you can read it. But this is in simple random samples of size 6. So if this is the case, the sample mean length of human pregnancies will typically vary 6.532 from the true mean, from the population mean of 266. So that's what it actually means. Then I want to find the probability that the average pregnancy length for women exceeds 270. So I'm still talking about over 270, but again, this is now a sample of 6 pregnant women. This is going to be far less likely than it is for a single individual woman. But again, just like with the population proportions that we were looking at before, you have to confirm that this is normally distributed before you use a normal distribution. So I'm just going to note, hey, the population was normally distributed, so my sampling distribution will also be normally distributed. So don't check the large counts, but you do check the shape of the population. So I still have, where am I going to put this? Still have a normally distributed population. I'm going to sketch that the center is still at 266, but now it is shrunk down dramatically. My standard deviation is only 6.532. And these are not individual measurements of my population. These are average pregnancy lengths. Average pregnancy length. So now we can see that 270, it's not beyond one standard deviation still, but it's a whole heck of a lot further away than just a fourth of a standard deviation. So I'm going to just kind of sketch it here-ish. So I'm still finding the probability of being over 270. It's just not going to be as much in that space as it was before. I am going to be lazy. Oh, no, I'm not, because you can't read what I wrote. That's annoying. I want to be lazy, but I can't. I'm finding the probability that my average will be more than 270. So just like before, I'm still using normal CDF. Just like before, my left shading began at 270. The upper was supposed to be infinity, so instead I'll just pick a big number. The means were the same, but now my standard deviation has shrunk down to 6.532, which means it's less likely for this to occur, and it's actually 0.2701. So still not statistically unusual, but it's not a common thing. So I did want to go over the, like I said, I will clean up what I had written in on part A because I scribbled all over it, and this will be uploaded to the class calendar so that if you need some time to write this down other than what I have in the video, you can go find